about real-time. In Chapter B, I pointed out that real-time was in focus when choosing a computer for laboratory use in the 70s. And in the introduction, we saw this OH page where a response time of 100 milliseconds was mentioned, as you see here. But with regard to analyzed instrumentation communication, the real-time requirement was not so strict in the 80s. Already in the start of the 80s, the analyzed instruments had more data memory. The instrument could store data or look up in their own memory for getting information or which analysis to perform, so they were not so acutely depending on external conditions. You could say that the strict real-time process, in a way, has moved into the instruments. But one day it will happen, when the system is hard-loaded, that all 20 instruments send a request for data or send data to the computer at the same time. So there must still be a short response time all over in the system, but not in the 100 milliseconds range. So, to ensure real-time communication when there were many large instruments, we made small, high-priority drivers, that is, memory-resistant self-contained programs with short processing time, combined with FIVO in the 12C40D multiplexers. Received data is transferred to separate so-called display file for each instrument, a file which was locked only for a very short time intervals. And of course, we had the HB1000 and the RTE real-time facilities. Real-time operation of analog instruments was never a problem with the HB1000. However, short response time always in all processes was important in a laboratory environment. But to see how the system lives up to these requirements, let us see how the 1000 system was loaded. Here are some statistics from '98, where we can see on the left part of this page that requisitions start to arrive to the lab in larger quantities around 8 a.m. and the input peaks around 9 a.m. and 11 a.m. with about 500 requisitions per hour. Note, this was in '98, and the production around the year 2005 was 1.8 times greater. At the same time as the requisition appear, the main part of the samples come to the laboratory. The sample tubes goes on to the instrument. It is therefore a must that the requisition data are updated without delay, as the analyzed instrument can look up in the system to see what they have to do, as well as dispatch of work orders for the instruments must be done without delay. The condition surrounding input with OMR requisition, etc., is described in Chapter C. The conditions surrounding the register structure and approach from the instrument side are described in the next chapter. About the results. On the right, you see a corresponding overview of received analyzed results, where you can see the top is about 1 to 2 hours later than for the requisition part, with a peak approximately at 1:30 p.m., approximately 5,000 results per hour. Remember, that was in '98. Real-time condition around the instrument is dealt with in the previous chapter. The register structure is dealt with in the following chapter. About cumulating answers. The cumulating answers has to be printed and distributed within a short time, 1 to 1.5 hours for standard answers. Urgent and expedite answers had special procedures. In '98, approximately 130,000 answers were printed before the end of the late afternoon. If 130,000 results must be printed in about 1.5 hours, that is a patient result per 41 milliseconds. With a production as in 2005, that is only 23 milliseconds per result, a short time with an archive on disk. Considering all the other activities the system has to take care of simultaneously. About table lookup. The many table lookups, for example for analyze name, units and age and pregnancy-dependent intervals, etc., were done via the relatively small analyze table being resident as described in the previous section of program with same resources. Moreover, the table content were sorted according to how frequently the individual entries were used, so that the many 100,000 of lookups in memory could be very, very short. A note about the many cumulative answers. Where there are around 1,500 to 3,000 acquisitions per day, then the 40% of data was from the private doctors in the county and not quite as urgent. But why do so many result replies need to be printed? This is partly due to the fact that a requisition when the answer is received often results in a printout with more than 100 results. This is because if a patient has early data in the system, then the last 10 requisition with answer is often printed. That is a full page. Thus, the doctor often only needs to see that one page, and all of the same type of analyses on this page are on the same line. How the register structure supports these requirements appears in the next chapter. A register structure. The structure used on the HP1000 RTE system was partly a system built around the RTE A file system called the work register, partly a system built around the image2 network database. The work register could contain approximately 100,000 patient results, a portion of which was related to the daily production of the work register was approximately 40,000 results. The database contained around 998 7 million results. It was later expanded to 21 million results. The two registers were integrated in the sense that data could be transferred from the work register to the database and from the database to the work registers. When a person-related searching and cumulative results printing, data was retrieved from both registers. There were both advantages and disadvantages to the two forms of registers. Historically speaking, the work register was developed and used before the image2 database was announced. Both systems was relatively simple, that is, transparent structures, understood in such a way that it was possible by simple calculation to see approximately how many disk-related entries were needed to store and read in the registers. But to better understand condition, it may be appropriate first to look at how the HP1000 and RTE, and for that matter also RTEIII, in principle processes data files. Here is a picture from the RTE program's reference manual, which explains some of the main principles. There are several different types of file. Here I will only describe two, called the type 1 and the type 2 files. When a file is opened, a small block of data, 16 words, is not shown. it's loaded, which contains the control data for the file. But now let us look at the type 1 file. If you read or write in a type 1 file, read or write is directly from the blocks in the disk to the user's memory buffer. For example, this is exploited by reading an index file up containing an entire index for all date requisitions, 3,400 records, in one disk reading. The buffer is not, as shown in the picture, limited to 128 words. The limitation of the buffer is the data space, in practice approximately 25,000 words. For example, this is used when a data block, typical 60 results, were transferred from the so-called display files and had to be entered into the work registers. All pointers to 60 result records could thus be found for the requisition in one disk lookup, and then to link directly to all result records. This index function on only that could be in a separate program, as previously mentioned, a program with saved resources. Let us look at the type 2 file. The type 2 file, for example, reads a large block into the DCB buffer, shown here as a 121-word buffer, but it could be much larger. But it takes space up in the user data area. But it could, for example, contain all the results for a requisition. Reading or writing one or more results belonging to a requisition could therefore be performed by only one read-write entry. Many logical access, that is only entries in the DCB buffer, followed by only one physical access. Multi-program access to several DCB buffer was handled via so-called POST, a physical read-write, and semaphore and coulomb. I'll not go into that now. Instead, short, it can be said that the advantage of the work registers mainly consists in the fact that the mechanical logical disk read-write will reduce to a few physical disk access. This due to the size of the DCB buffers related to the type 2 files, and that the result record was most often physically collected, and that the index could be read in only one physical disk lookup. The disadvantage of the work registers was the limited size, and it had to be cleaned up once a day. About Image 2. Image 2 database was constructed with relatively many search keys. See the diagram here. The triangle above are the search hash index registers. If you look up in such an index, you get the pointer to the current record in the registers via an algorithm. For example, the person registration number is called, you get the pointer to a record in the file with this number, and all records with the same number are linked in the chain. As you can see, there are 6 different keys for the requisition file. An example, all requisitions with the same department code are linked together. The result of that is that for each requisition record, sync links forward and sync links backward are inserted in each record. This gives many links. Submitting a requisition and 10 result is calculated at approximately 155 disk updates. It is a mix of physical and logical updates inside the database system. The database is not, with so many search keys, useful for quickly creating requisition result records. In the work register, a corresponding update requires only 4.5 physical disk updates. On the other hand, the register is very, very small. The conditions for searching are completely different. Here the person registration number is obtained via the hash index, the pointer to the patient requisition record. The relevant records are linked together in date order when created. This is a database feature. That is the order to be used for searching and cumulate printing. The read access can hardly be done faster in a large disk-based archive. However, a search in the work register is approximately twice as fast, which is due to, as mentioned, to the result record are physically collected. A conclusion. In line with the above, the work register is particularly fast when it comes to creating data as well to enter data response from online connections, but also when fast searching. Image 2 is quick to read out data and, as mentioned, and can contain up to 21 million results. I should mention that deleting of data in image 2 and update from the working registers was at night with an open running system. This was a bit about how the file system and image 2 were used on the HP 1000A and RTE A. First, a little about why and how this statistic project, which was mentioned earlier, started in '98, and a bit about LSP. See the picture. Around '94, we were looking at whether we could connect all the hospital's departments with PCs in the hospital with Labka on the HP 1000 system. That is, more than 1000 PCs to one HP 1000. We completed such a solution in '97. It came to be called the LSP Labka Hospital Package. In '98, we would like to deliver this system to our largest installation, which at that time had a production of about 3.5 million analyses annually. Also, as previously mentioned, print out 130,000 cumulative results daily, the largest of our installations. The production was distributed physically among 4 hospitals and also served the county general practitioners. But first we had to convince the hospital that the HP 1000 system could also support the many more 1,000 PCs in the ward with a new procedure, where requisition and search has to be done from the many PC terminals in the hospital wards, and many searches has to be expected. This was the reason for the extension measurement on the April 21 in '98 on the HP 1000 RTE A. The measurement was carried out by adding extra programs on top of the ongoing production on a busy day to simulate the extra load that the LSP system would add. Loading was carried out in such a way that when loading programs, it ran at the same time as the production. They will be loaded accidentally with the additional load as CPU load, disk load, that is read-write in the corresponding file as in the work register, and logging the same semaphore, the NRNQs, at the running system. Priorities for the load programs were set to the same as the running video terminal programs. The artificial load program could also measure total time corresponding approximately to updating of a requisition, CPU time, disk time, and schedule time. A detailed report of the mission was drawn up. This is a picture from the report. Note especially schedule time. Almost all times are below 40 milliseconds. Amazing, amazing real-time HP 1000 RTEA. The result of the measurement was the implementation of LSP, which resulted in approximately 2,000 PC terminals connected, located at the 4 hospitals. I would like to try to describe a bit about the LSP later. That is, it is only planned. If you want to learn more about the Labka and the HP1000, see the page guidelines here. Here you can also read more about LSP and perhaps watch the demo videos. The LSP videos are a kind of video playlist, DVD broadcasted as an appetizer in '98.